Greetings. We're continuing our discussion from video lecture 3 on Laplace transform using the definition to evaluate Laplace transform. We have a few more examples left to look at, so then we can move on in finding Laplace transform by using techniques, not just necessarily a definition. Just so that we recall, the Laplace transform of a function by definition is the improper integral 0 to infinity of the kernel e to the minus st times the function itself, f of t dt. Now we've talked about some basic Laplace transforms, and now let's talk about the Laplace transform of trigonometric functions. So I'm looking at finding the Laplace transform of cosine of at. Now by definition, Laplace transform of cosine of at is the integral from 0 to infinity of the kernel multiplied by the function dt. Now, that is not a trivial integration by parts. I mean, even if you use a tabular method and you write e to the minus st and cosine of at, and then take derivatives of e to the minus st, so minus s e to the minus st, s squared e to the minus st, s cubed, s cubed negative e to the minus st. And you notice that the derivative doesn't end. So using the tabular method is nice, but it only works if the function in which you're differentiating has a terminating derivative. And then you could integrate cosine of at and keep going forever. And so you've done this in second semester calculus, and even if you do it with u dv, you still have to do integration by parts a whole bunch of times to get to the answer. So by no means it's a trivial integration by parts process. Now sometimes we could use, thank God to the gift of mathematicians from the past, some tricks that will possibly make the integration easier. Now, and apparently there is such trick for this one. Now if you recall the Euler's identity or Euler's formula and the inverse Euler formula, you know from your pre-calculus class, I assume, or even in second semester calculus, that you could write cosine of at as a linear combination of exponentials. We call that the inverse Euler's formula. And there's some formulas, same thing for cosine of at, for sine of at, for cos of at, so sinh of at. So you could always write a trigonometric function using inverse Euler formula as a linear combination of exponentials. Now you see, if I do that, then assuming that I've been asked to find a Laplace transform of cosine of at, I can just write cosine of at as e to the iat plus e to the minus iat divided by 2. And then I can separate those because, you know, Laplace transform is a linear operator. So I could write this as 1/2 Laplace transform of e to the iat plus 1/2 Laplace transform of e to the minus iat now equals 1/2. Now Laplace transform of e to the iat, we already know that from the previous video lecture. We've already done the Laplace transform of an exponential using the definition, and we remember that the Laplace transform of e to the at is 1/s minus a. So here I can just look at Laplace transform of e to the iat, and I know without even integration or using the definition, which is something we eventually going to have to start working with, meaning finding Laplace transforms without necessarily using the definition, by what we remember what they were. We can write the Laplace transform of e to the iat, which is 1/s minus ia, I complex number, plus 1/2. You see, it's so simple, you don't need to do any integration whatsoever. And Laplace transform of e to the minus iat is 1/s plus ia. Now if I factor out a 1/2 and find a common denominator, s minus ia, s plus ia is s squared minus I squared a squared, which is s squared because I squared is minus 1, plus a squared. I'm skipping over the trivial algebra. And your numerator will be s plus ia plus s minus ia. And now if I simplify this further, I have s squared plus a squared And here the IA's cancel, so I have 2s. And if I cancel out the s's, the 2's, then I'll end up with s divided by s squared plus a squared, which is the very definition of the Laplace transform of cosine of at. So you noticed I found the Laplace transform of cosine of at without doing any integration whatsoever. So this is a very nice method of finding Laplace transform of trigonometric functions if someone's asking you to use the definition. So let's see, I can bring you to this page where I've put down all the 4 basic fundamental trigonometric functions: Laplace transform of cosine of at, sine of at, cos of at, and sinh of at. And I've also written the Laplace transform for each one for you. So obviously you have to memorize these, but you should know how to find the Laplace transform of each one using what I just showed you. So I've done this for the cosine for you on the previous page, and you should do the same thing for the sine, cos, and sinh. All you have to do is find the Laplace transform of sine of at, and then convert sine of at and rewrite it as its exponential counterpart using inverse Euler identity, and write it as e to the iat minus e to the minus iat, and divide by 2. So you could go ahead and actually do the separation and use the linearity of a Laplace transform to go ahead and do it as simply as I did it for the cosine on the previous page. Now, so far we've looked at Laplace transform of a few fundamental functions. We looked at Laplace transform of 1, t squared, t cubed, t to the n, sine, cosine, and the basic exponential. We've used definitions to do it, and I would strongly recommend that you memorize these fundamental Laplace transforms, because on the next video, when we start evaluating Laplace transforms using techniques and previous some more fundamental well-known Laplace transforms, you're going to need to remember all of these. So for any student of differential equations, it is usually expected for you to at least remember these fundamental Laplace transforms, because you're going to have to obviously use this beyond this course in your engineering courses. So go ahead and memorize these Laplace transforms, and you must be able to verify these Laplace transforms using the definition. And just a note, I've brought in what's called the gamma functions. You see the Laplace transform of t to the n, as I showed you previously, and I showed you how it works and why it works. Given that it's n factorial over s to the n plus 1, you see that's only true if n is a whole number, is an integer. It's not a decimal or a terminating or non-terminating decimal. And it only works if n is 1, 2, 3, 4, 5, 6. Now, what if n is 1.5? What if n is not a set of counting numbers, but it's a set of real numbers? Well, then this Laplace transform of t to the n, instead of being defined as n factorial over s to the n minus 1, is then defined as a new creature called gamma functions, where by definition, that's what a gamma function is. You don't need to know this for this course. I just wanted to put it here because it's because you could simply ask, what if it wasn't 1, 2, 3? What if it was like 1.56? Then how would you find the Laplace transform of t to the power of 1.56? Well, you do it using gamma functions. But it is not required for this course. If you like to read more about it, you can just go online and do some research on what gamma functions are. I also want to present to you, before we wrap up finding Laplace transform using definitions, that you could also find Laplace transform of piecewise defined functions. Using the definition is quite simple. Most of it is 0, for example, in exercise 1. So if somebody says find a Laplace transform of f of t, you see f of t integration-wise is from 0 to 3, and then from 3 to infinity. You see it breaks. Now from 0 to 3, the integrand is 0. Okay, so even if I multiply it by e to the minus st, which is the kernel, multiplied by 0, this integral will just be 0. So I'll only be left with having to integrate 2 times the kernel e to the minus st dt, which is a quite simple integral. evaluated between 3 to infinity. So I just wanted to show you with this page that finding the Laplace transform of piecewise defined functions is really no different than finding the Laplace transform of any basic function using the definition. So you should be practicing fundamentally as being the primary objective of a student that's learning Laplace transform is to understand what Laplace transform is, and the fact that it's a linear operator and the restrictions on functions in which you could find a Laplace transform for, and also then practice finding the Laplace transform using the definition. Thank you, and I'll see you guys on the next video lecture.